Everybody. And hello, everybody, and welcome to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. It's been a long time since we've gone live like this, and I am so happy to be talking to you. Now, I got to go ahead and shut off a few extra noises that are echoing in my ear, and I know that they're real noises because the voices in my head usually have British accents. So I knew that when I was hearing noises, it had to be coming from some other source. In any event, we're so glad to be here with you. You know, in my day job, I teach at Towson University, where I'm also the planetarium director. And one of the reasons we haven't been doing live streams on Launchpad is because I've been busy trying to put together like actual planetarium shows in the dome, that sort of thing. And we were going to do a presentation tonight when things happened and they told us all to go home. And that's great because now that we're all here, we can all talk about the launch of the James Webb Space Telescope together. And I'm so excited to tell you about not one, not two, but three amazing guests that I have. First of all, before I get to my guests, I'd like to say hi. Just a quick few shout outs. We have Jenna Hess is here. Hey, I think she's a student of mine. James Dugan. Oh, it's always great to see you. Paul Peck, Drywall Tube is here. Lanny Waitsman from Illinois is here. This is great to see all you guys. And if you're catching this show from out of town, go ahead and leave a chat and a comment of where you're joining us from. And if you would also like to share this stream with others, feel free to put it out on Twitter, Facebook, whatever interwebs you want to use. But I am so glad to have all of you here. So we are T-minus 1 week-ish from the launch of the James Webb Space Telescope. NASA hasn't made a formal announcement yet, but before we were down to no earlier than December 24th, which will make the launch window kind of interesting because I understand now they're going to have to coordinate the launch window with with Santa's flight plan. But there's been just a lot of excitement. I know astronomers around the world have been very, very good this year. And, as a matter of fact, even XKCD memorialized this with the Astronomers Advent Calendar, which we're really excited about. So let me introduce to you my guests. And I think, yep, there we are. We have two of my colleagues from Towson University and one from ESA. We have Parviz Ghavamian, another professor here of astronomy at Towson University, Keilan Koch, an astronomer at Towson University, and Macarena Garcia Marin from ESA and also at the Space Telescope Science Institute, where they are going to be flying the James Webb Space Telescope. Good evening, everybody, and sorry about that. We'll just go ahead and get Parviz in here really quick. We had a few little hiccups. There we are. Yeah. It's great to see you guys. Thank you so much for coming in tonight.
Thank you.
Thank you for having us. Thank you for joining everybody online.
It's great. We have folks from New South Wales, Australia, so that's wonderful.
Oh, wow.
So we have quite a lot to talk about tonight. Namely, by now I think everybody here is kind of aware that the James Webb Space Telescope is a thing. And I thought what we could do is do something a little bit different because we can talk a little bit about where James Webb fits in with the context of the history of telescopes and why we even need to build this incredibly beautiful yet nerve-wrackingly complex instrument. And then we'll talk about some of the science that one of our guests right here is going to be doing, and another guest of ours is going to be doing as well, including some of the instrumentation. So, Parviz, I wanted to ask you if you could tell us and share with us a little bit about, why Webb is important and just how telescopes work in general. Just can you make us all smart on how this all works?
Well, that's a great question, Chris. And the main function of a telescope, which I'm going to be talking about in my talk here, is that it's supposed to make things look brighter and larger and give you better resolution to be able to make out fine detail. These are things that you would never be able to make out with your own eye. And what's more, telescopes are also supposed to look at wavelength ranges, at least modern ones, that we never were able to look at before, like infrared or X-rays. And they mainly work by either reflecting if you have a mirror, or by focusing with bending if you have a lens, the light into an image of something. And so this has been going on for a long time, and I'm going to give in my little talk here. I'm going to tell you a little bit about where we started from and how we ended up where we are today with this giant, impressive telescope that's about to go up. So what I'm going to do is, okay, so when Chris said, hey, do you want to say a word or two? I didn't realize he was saying launch into your talk now.
Go for it, Parviz. I'm sorry.
So I am. Anyway, so I'm Parviz Ghavamian. I'm at Towson. I wanted to tell you a little bit about this telescope. So everyone knows about the Hubble, and it's been up in orbit for almost 30 years. And it had no sooner been put out up into orbit before astronomers were already thinking about the next telescope that they wanted to build, and it's taken them 30 long years to build this thing. And one of the main reasons is that it's really required inventing a lot of new technology along the way to do these specialized tasks that they need to do. And there have been so many delays and other sort of cost-related issues that have come up, and so everything takes 2 or 3 times longer than you think they will. But so what I want to do is first tell you a little bit about how we got to where we are today. So let's start a little bit with the history here of the telescope. So this is a little diagram, a nice etching that was made by Adriaan van de Ven in a book in the Netherlands that he published back in 1624 in Middelburg. And here there's a man holding what looks like a telescope, and it's one of the first depictions of something like this. And his picture was based upon something that was going on just down the street from him. There was an optician, an expert at making lenses and eyeglasses, and his name was Hans Lippershey, sometimes spelled Lipperhay, the different pronunciations there. And he had already been experimenting with what happens if you take a couple of lenses and put them together and look at something far away. What do you get? And it was an idea that was kind of in the air. And he tried to actually patent this invention of his with the Dutch ministry, and they didn't accept it because they said this idea seems to be kind of in the air right now, kind of like the Seinfeld episode where Elaine is saying that there's this idea of eating the central part of the donut, or taking the top off the muffin and eating the bottom. That's an idea that's in the air, she said. And so same thing over here. And the purpose of this work that Lippershey was doing was the purpose that he said was for seeing things far away as if they were nearby. And so that's always been the purpose of a telescope. And so barely a few years later, and we're talking like 1610 or so, already Galileo down in Italy, he already had his hands on this invention, and he set about trying to improve on it. And he's known as being one of the first. There may have been another scientist, a British scientist, who also did at the same time use it for looking at the sky. He was one of the first to use a telescope to look at things out in the heavens. And what you see here is his actual telescope that he built, and it's on display in the museum over here. I believe it's in Florence. And so it seems like a very simple kind of a device, and indeed it is. So these telescopes use lenses. So here's a cross-sectional picture of a lens, and lenses have what we call an aperture. That's the diameter of a lens, and the idea is that the light comes together and it produces a little image over there where the rays come together, and this bending of light is called refraction. And the distance behind the lens where the image is formed from something that's far away is what we call the focal length. And the focal length is something that's very specific to a lens or to a mirror, and it's one of the most important defining characteristics. So the idea is that, okay, that's great, you have a lens, but why do you need 2 of them, like Lippershey was saying? Well, the idea is if you have one of these lenses here and you have a focal point that's in front of and behind that, the idea is that the light from some distant object, the rays enter into the lens and they come together into a little focus over here like this, and you get a nice little image like this. And what's great about the image is that it's a lot brighter, because all of these rays that normally would not have come together are forced to come together, and you focus them into a bright sort of a central source like this. But one of the problems, though, is that this thing is still very, very tiny. And so what you need to do is you need to bring in another lens and put its focal point just inside that of this outer one. And the idea is that the light from this bright image here it forms an object for this second lens over here. And so as these rays pass through this second lens, then the idea is that it makes, if you put your eye over there, it makes a very large image of the object. And so really what you're doing here is you're using one lens to collect the light and bring it to make a bright image, and then you're using the other one to magnify it. So it's kind of like a light bucket plus a magnifying glass. And so the purpose when you use things like this is to make things look bigger and make things look brighter. These are very important things, but also you have to resolve a lot more detail. And that's, it turns out, is one of the most important modern definitions of what makes a good telescope. And James Webb is going to have like this in very, very high amounts. So Galileo took his lenses together, and he actually ended up revolutionizing astronomy. And some of the things he did, which were as groundbreaking in his day as James Webb is going to be in ours, was that he was able to make out the phases here of Venus. And here are some of the drawings that he had in his very own book. And he was one of the main scientist who was able to figure out that the phases of Venus can only be explained if Venus is going around the sun from the perspective of Earth, and that Venus couldn't possibly be going around the Earth, and showing all of these. So this shows how inventing a new instrument can lead to incredible revolutions in astronomical discoveries. He also discovered that Jupiter has moons, and so here are some drawings showing the different moons going around the edge of Jupiter like this. Here's what a modern picture would look like. Here's Jupiter with all of its moons, and he was the first one to notice that these moons go around Jupiter. And in looking at that, he said, wow, if those moons can go around Jupiter, then that kind of makes you think everything can't possibly be going around the Earth. And so that sort of weakened the whole sense of Earth being the center of everything. And so this shows you that when you have the right kind of instrument, you can do some incredible things. Now, one problem, and this is what led people to go away from refracting telescopes, one of the reasons why is that if you take, here's your main objective lens, and then here's your eyepiece like this. If you send in white light over here, the problem is that there's this little thing called dispersion that happens within lenses, where the red light is going to come to a focus over here and is going to produce a nice image like this, but then the green component of this light comes to a focus at a different point behind the lens, a little bit closer to it, and so it's going to make a slightly different sized image. And then blue light, even shorter wavelength light, comes to a focus at a different distance. And so all these different color components of light, they all have different focal lengths in effect. And so you end up with this really blurry looking image that has these colored halos around it, unless you can correct it. And so here's a picture, for example, of the moon that was taken with all of the corrections fixed. But if you don't fix them, you get these nasty looking halos, these colored halos around the moon. And so these are all things that are disadvantages of using refracting telescopes, and they're expensive to fix. And so it was Isaac Newton who came along and said, well, maybe we can get around this this is called chromatic aberration. Maybe we can get around this by using mirrors to reflect light and to make the images. And so this is an actual, this is Newton's actual telescope in the museum in the UK that shows how he set this thing up. And the idea was to use mirrors to reflect and focus the light instead of lenses. And so the way this works is that if you look at a side cut of this, here's the mirror of the telescope, the shiny side like that, and light comes in down this tube, down the side over here, and reflects off the mirror and comes over here to this little focal point. And this main mirror is called the primary mirror, and then the diameter of the mirror that tells you how much light it gathers is called the aperture, and then that's the focus over there. So it's very much similar to a lens telescope. You have focal lengths and apertures and focus, but it reflects light. Now, here's one problem. When you look at this, you'll notice that, well, if you come and you put your little detector or your camera in here, it's going to block some of the light that's coming in down this tube. And so the idea is that you want to try and take this light and send it somewhere else where you can image it. And so one other design that they've used for telescopes is something called a Casa reflector, and it's named after a Frenchman named Casa. And so the idea is that when light reflects off the scope, instead of letting it come to a focus over here, you stick an extra mirror. It's called a secondary mirror, and that mirror reflects that light back through a hole at the back, at the base of the telescope in the main mirror, like that. And so then that light passes through the back, and you can set up your camera or take your pictures however which way you want to. And so so this is one of the really important ways that scopes work. And so zooming ahead to our launch now, the James Webb Space Telescope has a very similar kind of design, even though it's the largest space telescope ever deployed. So here, there you have these mirrors like this, and the light comes in, reflects off the mirrors, and hits the secondary here, and then that light is then sent in through this hole at the back. And behind the main mirror of James Webb is this large, very expensive and very dear to astronomers assembly of instruments where all the brains and the science work of James Webb is done. This is the Integrated Science Instrument Module. And so some of the best detectors that we have are in there. And there are a number of other components here on James Webb that we'll talk about a little bit more. The most important one is the sun shield that's supposed to stop it from getting any sun. So we'll discuss the importance of that more in just a moment. So what does James Webb do? Well, in order to explain one of its most important functions, we want to talk about resolution. So to talk about resolution, let's get a little bit sciencey here. So in astronomy, you oftentimes can't directly measure distances to things. You measure angular sizes. So if you think here's a circle, and if you go all the way around in a circle, that's 360 degrees. And now if you take each one of those little degrees over here and you chop it up into 60 pieces, these are called arc minutes. This is 60 pieces. And then each one of these little arc minutes, if you divide that into what we call 60 arc seconds, then you have some really nice fine scale smaller pieces that you can measure degrees by. So there's, if you do the math here, there's 3,600 arc seconds in 1 degree in one of these objects. And so believe it or not, astronomers oftentimes have to measure things that are a small fraction of an arc second in size on the sky. So let's give some sense about angular resolution. If you take a soccer ball like this and you imagine you put the soccer ball really far away, and imagine you put it 45 kilometers away from you, then given a standard soccer ball size, that would subtend an angle of about 1 arc second, or 1/3600th of a degree. So arc seconds are oftentimes things that astronomers are concerned with measuring. So if you want to define then something called angular resolution, in order to define this, you want to take the observation wavelength and you divide it by the telescope diameter, and the ratio of those two tell you what is the smallest angular thing that you can resolve over here. And so the larger the telescope aperture is, so the bigger this diameter is over here, the smaller the angular size that you can resolve. You want this angular resolution to be really small, like a very small number of arc seconds. And so this is telling you then if I put a soccer ball that far away where it's only 1 arc seconds, if you want to be able to resolve any detail on the soccer ball, you won't be able to with your naked eye, because the human eye, and someone has actually calculated this, the human eye, if you use this formula here, has a resolution of 20 arc seconds. That means that anything that is smaller or closer together than 20 arc seconds, your eye can't make out. It won't be able to resolve it. And so this tells you then that there's a limit to how far away something can be before you can make out any more detail on it. So this is one sort of a concrete example of angular resolution. And so this tells you then size matters. And the reason is that your telescope diameter, it matters. The bigger you make that, the smaller your angular resolution that number is, and you want that number small because that means you make out really small angles. Now, if you want to compare what, say, 2 close together stars would look like, here's another way you can talk about resolution. If you have a 1 meter telescope, so that's 1 meter diameter telescope there, it turns out that the minimum resolvable angle, if this is the wavelength you're observing, is about an arc second. So if you have 2 stars that are any closer together than an arc second, you won't be able to resolve them with a 1 meter telescope at this wavelength. But on the other hand, if you now triple the diameter of your scope, now you have a 3-meter telescope, now your minimum resolvable angle turns out to be only about 0.38 arc seconds. And so now these two stars, which were really close together, you can resolve them because they're just barely able to be made out. And so this tells you how when you use a telescope, that a larger telescope lets you really resolve finer detail on things. Now, one of the problems is that what I just described to you is this is the optimal case. It's called the diffraction limit. And it turns out that when you observe from the ground real stars in space, atmospheric turbulence causes a lot of trouble. So if you have, for example, light coming from far away and then entering the Earth's atmosphere, as that light front, so these straight lines are the wave fronts of light coming down, as they come down to the telescope, they're going to hit these pockets of air. And some of these pockets of air are denser than other pockets and warmer, and they're rising and falling and expanding and contracting. And so as the light passes through them, they almost act like little lenses. They bend the light around. And so each one is randomly bending and redirecting the light. And so by the time this light gets to your telescope, its trajectory has been randomly jiggled and messed with by the turbulence in the air. And so when it hits your telescope and then comes to a focus, the field of view here, it looks like everything's been smeared out a little bit. And so this is an image of some stars that are really close together, and their separations are comparable to the amount of smearing that you are getting from the atmosphere. And so this kind of problem with the atmosphere, there's really no way to get away from it as long as you're over here on planet Earth. But once you go above the atmosphere, this problem goes away. So here, this is just a little handy plot that shows here's how opaque the atmosphere is. And if it's 100%, that means light doesn't make it through. So the light's coming from above and hitting the atmosphere. And here's all the different wavelength ranges that we know and love. And this rainbow here shows the range of visible light that we observe from the ground. And you'll notice down here from the ground, there's still a little bit of opaqueness to the atmosphere, but you can still see light from space. But when you get above the atmosphere, there's no more opaqueness, and it's completely transparent. The James Webb Space Telescope covers this wavelength range that starts right at the longest part of the visible spectrum and goes off to the mid-infrared. And this wavelength range over here, if you were from the ground, you would be having these walls in wavelength of obstruction from the atmosphere. You would not be able to see them. So one of the things James Webb is going to do is you put it above the atmosphere so it gets rid of the blurring, but it also gives you unfettered access to these wavelength regimes over here. And so James Webb is going to be complementary to Hubble because it's going to take what Hubble did and it's going to extend that to even longer wavelengths and really get very good imaging. So what does this really good imaging do for you? So if you have an image, and here's an example of one of the best images that we can take from the ground over here with this telescope. It's 8 meters, so that's approaching 30 feet in diameter. Despite having such a large aperture, you'll notice that the quality of this image from the ground is not as sharp as this telescope, as the Hubble telescope's image. And you'll notice that the Hubble telescope has only a diameter of around 2.4 meters, much smaller than Gemini. But you notice its spatial resolution, what I quoted earlier, resolvable detail, is much smaller. And so it can make out stars and features that are much, much smaller than what Gemini North makes out. And so this nebula looks a lot more spectacular from space with the Hubble. So this is what, if now you go to the infrared, this whole problem with resolving things gets worse because here's an example. If you look from the ground at, this is a star field in the plane of our galaxy in the visible band, you'll notice that there are a lot of stars that are very close together and you can make them out and they're very well resolved. But if you look at this exact same field of view like this in the infrared, you'll notice that a lot of these stars, you can't make them out. And in fact, many of them actually merge together to form single sources. So in the IR, and this is a side effect of the wavelength being longer, in the IR, even when you have like optimal conditions and no atmospheric smearing, you're still limited because a lot of these objects are just too close together to make out. And so what James Webb has done is they've improved on the optics as much as possible to try and exploit this as best they can to try and get the best resolution they can, things better than what you can get on the ground. So on top of a mountain here, the finest resolvable detail will be at best usually around 0.6 arc seconds, maybe 0.2. And so here's a star field showing a simulation of what the galactic plane would look like with this kind of detail that you could resolve. If you now instead look at James Webb, that same field, you would see many more sources resolved. And again, this is not an actual image. This is a simulation here of that same field that we just saw a moment ago. But you see how much of a difference it makes. Going from this to this is just such better imaging quality. And so James Webb is going to be able to have that kind of quality over here in the near infrared. So here's the other thing that James Webb brings, which everyone can appreciate. James Webb is made out of 18 of these mirrors like this. This is what they call a segmented parabolic mirror design. And so the shape of it, if you look from the side, the shape of the scope, the mirrors are laid out in this kind of like a parabolic type of shape. And each of these little mirrors here is made out of beryllium metal with a coating of gold. And this gold has been, people have realized it's not just valuable stuff, but it's also fantastically reflective, and you can polish it very finely to really get the best possible reflectivity that you can possibly have. And you'll notice James Webb is the mirror is a lot bigger than that of the Hubble, and it has considerably more light gathering capability. So here's a few words on where we're going to put the James Webb. And so here's Earth, and Earth is 150 million kilometers away from the sun in its orbit, and there's the moon there. And the plan is, if all goes right, on Christmas Eve, we're going to launch James Webb out over here to about 1.5 million kilometers away from the Earth. And we're going to station it over here at this point called L2, or the second Lagrangian point. And the reason why they're putting it all the way out there, one of them is to go somewhere where you're not so close to the Earth and the moon, because they produce a huge amount of infrared radiation, and you don't want to blind your telescope by being near those. But another thing you want to do is you want to put it in a place where the telescope is going to be stable and isn't going to be pulled by the Earth out of its orbit. And so these Lagrange points, there's actually 5 of them, and it was calculated by this French mathematician back in the 1700s. He found that there are 5 points. If you have a spacecraft and then 2 other bodies, that you can take that object or spacecraft and put it at 5 possible points, such that the pull of all of the objects on it all cancel out, and it can stay there in a stable orbit. And L2 here, it turns out the second Lagrange point is the only one that works, because it's the only one where you can block out the sun and the Earth and the moon all at the same time and look elsewhere for your infrared objects in the sky. And all the other points, that doesn't actually work. So the idea is that James Webb is going to be way out here, and it may seem weird that it's kind of upside down compared to Earth, but the idea is that the light from the sun is going to come and is going to be stopped by the sun shield here, and the telescope, which is on this side of it, is going to be completely shielded from all of that, and all of the light that you're going to see is going to be coming from stars hitting this, and as this thing goes in its orbit, it's going to be able to see the entire sky. And so this main part of the scope never ends up pointing at the sun or the Earth. It's always pointing away. So the actual orbit is a little more complicated than that. One thing about infrared telescopes is that they have to be kept cold. And in order to keep this telescope cold, you can't take these instruments in the integrated science module. You can't expose them to any sun or heat like that. And so what you need to do is always keep the Earth and the sun and the moon always on this far side of the shield. And so in order for this to work, it can't just sit over here at L2. It actually has to execute a little orbit over here that's about 1 million kilometers in diameter. It has to execute an orbit about this point as the whole thing is going around the sun. And in order to do that, it has to keep itself pointed in this direction at all times. And the reason why it does this movement is the Earth and the sun and the moon are all moving continually. And so you have to move this telescope too in order to keep them all behind the shield. And so this complicated motion is something they've programmed into the telescope. and they always allow the cold side over here that you see to be facing away from all of the heat from the sun and from the Earth and the moon, like that. So that's the idea. Here's a little video that shows how this actually works. So here's the 5 Lagrange points I was telling you about, and they're not putting Webb at any of these other ones because the sun would be there, but Webb is here. And so I'm going to run this video, and it shows how this works. So there's the moon going around the Earth, and then here is the point where the Webb Space Telescope is going to be orbiting around. And so you notice as it's going around, it's executing this nice little loop around that point, L2. And as it's doing that, the Earth and the moon and the sun are always being kept on the far side of that sun shield, so it never has to look at them. So all of the observing that the Webb telescope is doing at any time is doing it in a direction opposite from the sun. So here's some of the science instruments that this telescope has. Here, there are 4 of them, and our scientists here are going to tell us a little bit more about it. But there's one called NIRSpec that is supposed to be a fantastic, a very sensitive spectrometer. And then there's the FGS NIRIS that does both imaging and does some spectroscopy. And then there's NIRCam and MIRI, which are 2 other instruments. And MIRI happens to be the one that goes to the longest wavelengths. The other ones are all focused on the near infrared. And so here's a little bit of the science that we can do. Just a few words on this. One of the bits of science that Webb has been designed to do is to study objects that are very far away in the universe. And obviously, in order to do this, they have to be emitting in the infrared. So the way this works is, if you imagine galaxies in our universe, if we are sitting here at the center of this galaxy, all the other ones are moving away from us. This is the Hubble expansion, the Big Bang. As their light travels through space to us, the wavelengths of the light stretch out in all the billions of years that it takes for them to get to us. And so as the light is traveling to us from these galaxies, it's getting longer and longer. And so by the time it reaches Earth, we're going to need an infrared instrument to detect this light. And so that's one of the purposes of James Webb. So what James Webb's going to do is, these galaxies here that are up to 1 billion light years away, their light has been traveling through all history and coming to reach Earth here. And they're going to be able to detect and have very good spatial resolution with this light that was emitted 1 billion years ago, and that's from these galaxies that are just beginning to form. The other kind of work that it's going to do, that James Webb is going to do, is to hunt for exoplanets. And so just one example of how this has been done before is with the Hubble Space Telescope, which is currently in orbit. It observed a star called HR 8799, and it used this technique called coronography, where you take a little black disk and you block out the light of the sun. Think of it as being like you're looking into the headlight of a car, and you're trying to see these fireflies that are around the car's headlight, but you need to block the headlight, so you have to put a shield in front of the headlight before you can see the bugs. So here are the bugs. These are the planets that are in orbit around the main star over here, and they were able to detect it by doing this work. And here's another example where there's another star in space known as Beta Pictoris that has a disk of material around it. They block the central star, and you can see the emission from the disk around the star as well. And so this is another thing that emits in the infrared and that you can study with James Webb. Here's another example, last example of science that you can do. Here's a ground-based image, and this was from a press release in 2015. And they were able to find, this is the closest star to Earth that they've been able to resolve a really giant, like Super Jupiter type planet from. And this object over here, this Super Jupiter, has around 10 times the mass of our Jupiter, and it's almost 100 times the Earth-Sun distance away from its star. And they were able to, from the ground, take a spectrum of this, and they were able to determine that this Jupiter here, it has signs of water in it, and this may be important factors in how the planet evolves into being something similar to Jupiter now. And it turns out James Webb will analyze spectra from planets that are much, much closer than this. So we're talking about now planets that are orbiting like this, much, much closer to the parent star. Here, it would have been lost in the glare of the star from the ground. But when you go out into space in the infrared, it'll be able to go in and really resolve that in a way that no one's been able to before. So that's just a little bit on the kind of science you can do with this. This was the original when I originally made this talk. This is the 18th of December was supposed to be the launch date. That has now been scratched, and now it's on December 24th. And so the idea was to put the telescope here folded up like origami into this little shell, and this shell, I believe that it's already been put into there, is supposed to be completely closed off very soon, and it's to be launched on the 24th. And so we're waiting now to see what comes of this. There's been a lot of hopes and a lot of dreams riding on this, and we've done everything we can to try and ensure that it is successful when it goes into space. But no one knows exactly what's going to happen. Hopefully it's all going to be good news. So I think that'll pretty much end it for me, and I'll turn it back over to Chris.
Well, thank you, Parviz. That was a great summary of just the history of telescopes, why it's important, and how this is going to work, at least in the broadest strokes. But of course, there's a whole lot of details that have to work just exactly right in order for Webb to go. And I think that's one of the reasons why Webb has experienced a number of delays. It is the most complicated observatory we've ever built. I've been monitoring the comments as you were speaking, Parviz, and obviously I think the biggest question in everyone's mind is when is it going to launch? And right now it is scheduled to launch no earlier than December the 24th. And no earlier means just that, no earlier. It could be the 25th, it could be a couple days after that. But there's a lot riding. What's really riding on this mission isn't the cost or the technical risks, it's the science. That's what we are trying to do with it. That's why we spent 30 years developing and designing, and 2/3 of that time building this incredible telescope that Parviz just described for us. So what I wanted to do now is just talk a bit about some of the science that we're hoping to do with Webb. And to that end, Keilan Koch is, well, she's actually got a science program on the James Webb very first cycle, or basically the first year of observations. And as I understand it, you've got some exoplanets that you want to investigate with Webb. Is that right, Keilan?
Yes, in particular two, but I'll talk about them.
Well, let's have at it.
Awesome. Hi, everyone. I'm Keilan Koch, previously Keelan Wilcombe, as Parviz will attest. I'm a PhD candidate at UC San Diego, working with Professor Quinn Konopacki. I'm also an adjunct faculty member at Towson University and a visiting scientist at Spce Telescope that's in charge of James Webb. And I'm here to talk to you guys about cool exoplanet science that will be done with JWST. All right. To start, what are exoplanets? Well, a naive definition could be a planet that orbits a star that is not our sun. But the definition of the planet itself requires the object to orbit the sun, have enough mass for a spherical shape, and it has to have cleared its orbit. So outside of our solar system, there is no formal definition. Here's a photo of the Milky Way, our home galaxy. Billions of stars light it, including the entire southern and northern celestial sphere. Astronomers now believe that every single star in the galaxy has at least one planet. That means that there's something on order of 1 trillion planets in our galaxy alone, many of them in Earth's size range. So if there are this many exoplanets in the universe, we need to know how to define them and characterize them from low-mass stars, or brown dwarfs, and other objects. So how do we begin to define an exoplanet? There are two main thoughts on this. One, we can classify them based on how they formed. There are two main formation mechanisms that I'll go into a little later. We can also classify them based on mass. The International Astronomical Union has recommended 13 times the mass of Jupiter, the limit to fused deuterium, but we have exoplanets that are known to be up to 24 Jupiter masses. So we're in quite a predicament. The first exoplanets discovered were orbiting a pulsar, a rapidly rotating remnant of a dead star, in 1992. Pulsar 1257 plus 12b plus 12c and plus 12d. But thanks to the Name Exoworlds contest, these were rebranded in 2015 as Draugr, Skyrim, Poltergeist, and Phobator, respectively. The planets were 3 to 4 times the mass of Earth. It wasn't until 1995 that we discovered the first exoplanet orbiting a living star, 51 Pegasi b. 51 Peg b is half the size of Jupiter with an insane 4-day orbit. There are a bunch of different types of exoplanets. Super-Earths are potentially rocky planets that have a mass greater than Earth, but no more than 10 times the mass of Earth. Rocky Earths have a similar mass, radius, and temperature to that of Earth, orbiting within the habitable zone of their stars. Gas giants are similar to Jupiter, Saturn, Uranus, and Neptune. They are mostly comprised of hydrogen, helium, with possible rocky or icy cores. Hot Jupiters are gas giants that either formed very close to their host star or formed farther out and migrated inward, the most common type of exoplanet found. About 50% of all exoplanets are hot Jupiters. This is due to the fact that they are the easiest exoplanets to detect. Here are the main detection methods for finding exoplanets. We have radial velocity, transit, microlensing, astrometry, and direct imaging. Most of these methods are indirect ways to see if there is a planet. There is only one method to see the planet itself. Given that the planets are typically close to a star that is much more luminous than the planet, direct detection of exoplanets is extremely difficult. This means that the most confirmed exoplanets have been detected indirectly. They're going to the wobble. Let's see if I can get this playing for you guys. I don't know if it will though. Oh, we have the spinning beach ball of doom. All right, well, I'll talk about it a little bit.
That's
The
okay.
radial
Just
velocity, huh?
improvise and adapt.
Right, I know. I'm hoping that my spinning beach ball goes away. Oh, okay, it went away, but all right, let me try and play it again. If you can bring it back. Awesome, okay. I need to treat this computer very gently, apparently. All right, we're gonna press play and see if it moves. It worked earlier. All right. It has decided not to work. But the radial velocity method detects the motion of the star that is caused by the orbiting planet. This means that the planets pull on the star and tug it away from the center of mass. This is through the blue shifting and red shifting light coming from the star as it wobbles around the central point of the star. I'm gonna go to the next slide. Okay, the next slide is working, so that's a good sign.
Okay. All right, we can see it. We can see your slide, and it's playing now.
Yeah. You got the top right thing. I don't know why the videos worked earlier for me, but they just really don't want to work right now.
You're fine.
Okay. Great. The next method is the transit method. We can detect exoplanets as they pass in front of the star and cause a periodic dip in brightness. False positives are very common and quite difficult to identify. Transit depends highly on mass and is more sensitive to larger gas giants and hot Jupiters. As shown in the video that isn't playing or won't play. Can try, nope. Yep, it's just deciding not to work. All right. So we have a really exotic method of planet detection. So this method utilizes Einstein's theory of general relativity when a star in our own galaxy acts to lens the light from a more distant star that, from our perspective, passes behind the lensed star. What we observe in this case is an apparent increase in brightness that can last for tens of days. To an astronomer, a lensing event looks like a distant star that gradually gets brighter over the space of a month or so and then fades away. If the planet happens to be lensed, it looks like a brief blip of light that happens during the brightening and dimming process. Sometimes free-floating planets in space, ones that don't orbit a star, will cause quick microlensing events that astronomers will record. These objects give us an idea of how common these so-called rogue planets are in the galaxy. The animation on the right should have shown what an event looks like to a telescope. Okay. The motion of the star, that wobble, can also be visible as changes in the star's apparent position in the sky. Astrometry requires extremely precise optics and is especially hard to do from Earth's surface because of our atmosphere and how it distorts and bends the light. VB10b is the first planet detected by this method. Shown here is a figure showing the VB10 system versus the solar system. The host star is an M dwarf star and it is much, much smaller than our sun. The major problem astronomers face in trying to directly image exoplanets is that the stars they orbit are millions of times brighter than their planets. Direct imaging involves blocking the starlight from the host star to see the light from the companion. Direct imaging is more sensitive to younger objects that are still self-luminous, they have a large mass, and they orbit at very wide separations from their host stars. The first directly imaged multi-planet system is the HR 8799, a quite famous system, shown in a series of images taken at the Keck Observatory in Mauna Kea, that's in Hawaii. HR 8799 is 129 light years away and is actually in the constellation of Pegasus. By coincidence, it is quite close to the star 51 Pegasi and the first ever exoplanet around a living star. It is less than 60 million years old, and it's almost 5 times brighter than our sun. The closest planet orbits every 40 years, and the furthest orbits every 400 years. JWST will attempt to answer these questions. Do planets in a planetary system form in place, or do they travel inwards after forming in the outer reaches of the system? How do planets reach their ultimate orbits? How do large planets affect the smaller planets, in solar systems like our own as well? From our own solar system to distant star systems, what can we understand about planet formation, evolution, and the suitability of planets as habitats? The main way astronomers try to answer these questions is by studying the atmospheres of exoplanets and look for tracers of formation and evolution. To assess atmospheres, we look at the light to see what molecules are present. This is called spectroscopy. When a planet passes in front of a star, the light passes through the planet's atmosphere. If, for example, the planet has sodium in its atmosphere, the spectrum of the star added to that of the planet, we will have what is called an absorption line in place for the spectra where we would expect to see sodium as shown in the graphic. This is because different elements and molecules absorb light at characteristic energies, and this is how we know where in a spectrum we might expect to see the signature of sodium or methane or water if it is present. JWST will do transit spectroscopy just like the figure above or in front of you, and direct imaging spectroscopy. Direct imaging spectroscopy involves light coming from the planet itself, passing through the atmosphere so we can see dips in the spectra to show what molecules are in the atmosphere. Shown here is my actual data showing the planet Kappa Andromeda b and the spectra we get. That dip that you see in the spectra to the right is actually CO. So what now? The next step in directly imaging exoplanets is characterizing their spectra and extracting traces for formation pathways. Those formation pathways will help us better understand exoplanets and eventually develop a concrete definition of what they are. Metallicity and metal abundances provide hints towards how these planets formed. There are 2 main formation pathways, the core accretion scenario and the gravitational instability scenario. For core accretion, a core is accreted, and then runaway gas accretion creates the atmosphere. This will cause an enhanced metallicity in the atmosphere when we're looking at the spectra. In the gravitational instability scenario, clumps appear from the protoplanetary disk and gaseous planets collapse from those clumps. The metallicity in the atmosphere should be similar to the star that they formed around. Ground-based observations can only go so far. Shown here is a spectral plot from my very first paper, Welcome et al. 2020. The gray caterpillar-looking line is actually a computed atmospheric model spectra of the exoplanet Kappa and b that tries to fit all of the observed data. So the red, purple, blue, and orange dots and the black and blue lines. Notice that it doesn't fit all of the data perfectly. And there is a significant lack of data past 3 microns. Because of the thickness and the brightness of Earth's atmosphere at that wavelength range, we cannot access this information, just as Parviz pointed out. We are missing key pieces from the longer wavelengths, such as vertical mixing, which will displace methane, and cloud properties, because a lot of these objects have thick clouds. And as you can see, the photometry, or the single data points on this plot, can only constrain so much. In comes JWST's NIRSpec, one of the instruments. NIRSpec is a near-infrared integral field spectrograph that operates within the range of 1 to 5 microns. It will give us access to moderate resolution, so about 2700. Without atmospheric turbulence, there is minimal correction needed for the incoming wavefronts. So most of the starlight coming from the star will come from fluctuations in the optical systems and by spacecraft conditions, some things that we can actually model and perhaps control. So here comes the fun part. I am the principal investigator of a Cycle 1 program to image the new multi-planet system TYC 8998-760, or they're trying to rename it YSIS-1, which I think is a lot easier to talk about. We will target those 2 Jovian exoplanets. They're about Jupiter, hot gas, and hot Jupiter type planets. So we will obtain complete low resolution spectra from 1 to 12 microns using NIRSpec and MIRI, an instrument that will be talked about soon, and high resolution spectra from 3 to 5 microns using NIRSpec. Common age information environment of these 2 planets eliminates uncertainties that can actually plague comparisons between objects in different systems. The host star is also one of the lowest mass stars to host more than one exoplanet. Shown here are simulated data for the planned NIRSpec IFU pointing. So as you can see, the 2 little bright dots there are the 2 exoplanets. So we just need to point the instrument in one direction and we'll be able to get the spectra from both of them without having to move it around. Shown here are the expected spectra from my JWST Cycle 1 program, emphasizing the amount of spectral information gained from JWST. Note that these won't be models guessing with limited data points. All the lines in these plots represent actual data that we will get, and this will be the most comprehensive data set of an exoplanet to date. And we'll have 2 of them. But that's just my program. There are many other programs that will image exoplanets that I am involved in. We will observe several well-known exoplanets and brown dwarfs or small stars. GTO observations are guaranteed time observations for the people involved in creating the instruments for JWST. ERS are early release science programs that astronomers could apply to. And JWST will provide the first mid-infrared observations of many directly imaged companions with about 10 times more precise photometry, or those single data points that you saw. In conclusion, JWST will have a huge impact on exoplanet research. We will have more spectral coverage to complement ground-based efforts and to improve our atmospheric models. All in all, JWST will increase and improve our understanding of planet formation and evolution, and increase our understanding of our own solar system.
Thank you very much.
Thank you, guys.
Thank you very much. Soon to be Dr. Hoke. Appreciate it. This is a great talk. It's one thing we hear about, oh, it's got this feature, it's got that capability, but to actually get some insight as to how someone would use this telescope. I mean, this is why we built it. Actually, though, it's not strictly why we built it, because it was when it was conceived of, 30-some years ago. Exoplanets weren't really yet a thing, right? So you're kind of using this, which is great. That's exactly why we want to build JWST, to answer questions we hadn't even thought yet to ask. So hope you enjoy your telescope, Keilan.
Yeah. NIRSpec was definitely not made for direct imaging, but we're making it work.
Excellent. Well, there's a lot more to talk about. And this, of course, is not just a NASA mission. This is actually a very much an international collaboration. We've got the European Space Agency who have built an instrument and not for nothing are actually launching it for us, which is a huge win because I don't think it's going to work if you don't launch it, but I could be wrong. I'll have to defer to our next guest, Dr. Macarena Garcia Marin, who's an instrument scientist on what is literally the coolest instrument on the James Webb Spce Telescope. Maca, why are you and your instrument so cool?
Because we are so cold.
Oh, okay.
We'll talk about it in a little bit, but thank you so much for having me.
Sure, Maca. We're gonna go ahead and let Maca share her screen, and as she's doing that, we're gonna get everything working just exactly perfect. So, Maca, whenever you're ready, go right ahead and share your screen.
See if I can share my screen.
All right, well, let me go ahead and bring us back to this shot over here. And let's see, it doesn't look like anyone else is sharing their screen, so we're just going to work it out. You know, technical problems are nothing new in astronomy, so...
Definitely not.
Yeah.
But we know how to deal with them, right?
Exactly. Yeah, exactly. So what we could do is, really quick, we've had a number of questions coming in. And I think it might be really good just to take just a couple questions really quick. First of all, there was this question from Sergasi, also in the form of a super chat. Thank you so much, Sergasi. And he asked, why not launch JWST to ISS, the International Space Station, and monitor its unfolding? In case something goes wrong, it's possible to fix it. Only after then send it to L2. Yeah, that's a good idea. Why didn't we do that? Anybody want to take that one?
I'm going to guess something with orbital parameters because, you unfurl it there. I mean, the ISS is still in the outermost part of the Earth's atmosphere.
Yeah.
So the drag and all the other, and plus there's space junk floating around, et cetera. I don't know if you want a $10 billion instrument in harm's way. So that's just one guess.
Yeah. No, actually,
I agree with
that, believe it or not, in-orbit assembly was studied at one point. And what they really ultimately determined, to your point, is the point you just made, Parviz. You have atmospheric drag, but then you've also got all that junk, and it turns out that low Earth orbit is too dirty a place. It's too much contamination, and it's actually easier to build it on the ground where you can control the environment, and not only that, but then you don't have to add the extra mass needed to survive a second launch out to L2. So yeah, it was studied, it was looked into, and they found that it's actually going to be safer and easier to build it down here. And Parviz, this is probably going to your talk from earlier. How does JWST deal with the refracted light from the sun and the shield? Can you speak to that?
Refracted light from the sun. Refracted from what? Because refraction require
maybe
diffraction around the edges of the sun shield.
There is scattered light, but there is shielding around, and it is quite protected. We do have models to see how the scattered light may affect the instruments, but of course we have to launch, and part of it is how well and how tense the sun shield will deploy. But there are a number of models kind of predicting what the background of that signal will be.
Great. And Nick Zeno asked, did they make a duplicate Webb? I've got a paper model of one in my basement.
No, but that's a good question. Actually, I like that because we did build models for the instruments. Quite, at least for me, they're quite accurate ones, and we did have like thermal models for many things. At Northrop Grumman, they did build a model of the sun shield 3 times smaller, so they could actually evaluate the folding and unfolding and the building. So yeah, not a full one-to-one model, of course, but many models were built for testing and de-risking purposes.
And to Keelan, you were talking before about exoplanets. GFAT75 asked, will JWST be able to detect and classify exomoons as well? So exoplanets are no longer good enough. We want exomoons. What do you think?
Um, yeah, I know a lot of people actually that are studying exomoons, but it's in a very roundabout and completely indirect way. So, um, probably not using the same instruments that we'll be using for direct imaging, but you will be able to detect exomoons looking at different light curves using some of the other instruments.
Great. And actually, Etran asked, why can't all these planets be closer to us? It would make exploring so much easier. Keelan, why are the exoplanets too far away?
I don't know. But one cool thing is that one of the reasons why we have to go so far away to look at these planets is that the planets that are closer to us tend to be older. So their atmospheres are going to be more polluted by all the different chemical processes happening. So if we want to look at how things are forming, we want to go to the younger and younger ages of planets to try and see what their atmospheres look like before they get totally convoluted. But, if they're further away, harder to see, harder to get nicer data. So,
Great. Well, Maka, I see that you got your slides ready. Do you want to
Yes.
tell us a little bit more about how Webb's going to work and what it's going to do? So
Yeah,
let's roll
definitely.
it right on over to you, and here he is. What do you got?
Perfect. Thank you so much. And first of all, thank you so much, everybody online, for connecting today and following, what's going on with Webb and how excited we are all about it. So I'm going to talk a little bit about Webb and a little bit touch again on the instrument that Parviz presented so greatly, and then talk about the mirroring instrument, which is the one instrument I do work for. So this is a depiction of Webb, and Webb is the largest, most sophisticated and sensitive telescope we have ever launched in space, which means that really the best way of building it is to have a large collaboration. So in the case of Webb, we have three agencies: NASA, and United States is the main partner in the collaboration. Then we have the European Space Agency and the Canadian Space Agency. And this map, of course, is not for you to read any of these names, but it's just to get a feeling for the number of countries, about 13 countries, many institutions, and literally thousands of people behind these institutions working for more than 20 years to put this together. So a lot of effort and a lot of collaboration behind. So I wanted to start talking a little bit about the Hubble Space Telescope, which we all know very well. This is a very famous image of the Hubble Space Telescope. It's the Ultra Hubble Deep Field. And to give you an idea, this is about, if you take a straw and look at it through the straw, it's about that size in the sky, so very small. And it actually is a region of the sky that, if you look at it with your naked eye and with a normal telescope, it's just black. There is nothing there. So some years ago, they decided to use Hubble and observe this region during days and days and days, like several days of observations. And when they put it together, this is what they got. About 10,000 galaxies. Really, almost every little point of this image is a galaxy, each galaxy with thousands and thousands of stars in it. So if you then extrapolate to the entire sky, these are about more than 100 billion galaxies that we can see in the universe. And this is invisible light. Going back to Parviz's talk, if we think about the first galaxies that formed in the universe and the first stars and all those very primeval objects, they emitted light millions and millions of years ago, and that light travels towards us. And as it travels, the universe expands. So in that process of travel plus expansion, the light shifts to the infrared, and that is why it is so key for progressing in astronomy and these studies of the primitive universe, to have an infrared observatory as sensitive as Webb. And really, the incredible thing is that Webb is going to look at a time in the universe about 13.5 billion years ago, and even more than that we've never seen before. We've seen before that, like older things. We've seen what happens after that with Hubble and some other observatories. We don't know what happened at that time. So it's really exciting to get the snapshot of that sort of mysterious original first galaxies and stars. This is another image of the Hubble, again taken in the optical, the visible light. And you can see this image is called the Pillars of Creation. And these are beautiful dust structures. It's called Pillars of Creation because behind the dust, a lot of stars are being formed. So it's a region of heavily active star formation. If you then look at the same image in the infrared, you see that the dust almost disappears. And that's the second great advantage of looking in the infrared, that you can go through the dust. And with Webb, we can go through the dust even better than in this image. So we're going to be able to see all this activity that's going on behind this dusty regions. It's going to be literally like lifting the veil or lifting the curtain that the dust sometimes puts in front of us. So with Webb, we are going to be able to see distant objects, like the very first like galaxies, dusty objects, what's behind the dusty objects, like star-forming regions, and also cold objects like planets that Keilan actually covered them beautifully, so we don't need to go into those details anymore. So these are the three sort of main advantages that we have with an observatory like Webb using the infrared. I want to talk a little bit about the infrared and in general the light. So light is a wave, and here you have the visible range, which is the light we can see with our eyes. And as you can see, it's really a small sliver of the whole spectrum of light. With light, we have gamma rays, X-ray, ultraviolet, visible, infrared, etc., etc. So there are many different types of light and with different energies and different colors. So when it comes to a study of astronomical objects, ideally what you want is to observe the same objects with different wavelengths, because by doing that, you actually understand all the different layers. Astronomical objects are almost like onions, if you will. They have layers, and with each of these different wavelengths, you can study one of those layers. And then when you have a multi-wavelength approach, you can actually understand the nature of the object and how it was created and how it evolved. So it's really important to get all this information. So with Webb, we're going to be able to see in the infrared between 0.5 and 28 microns, and that is a very large range that will contribute to many other observations we already have. And in the infrared, we do have a lot of different colors. So the infrared is a very interesting type of light. So this is an image of a firefighter surrounded by a very thick cloud of smoke. And in the visible light, you don't see anything, just see smoke. If you then switch to the infrared, this is what you see. You can actually see a person in the ground, you can see the firefighter. In the infrared, you're measuring the temperature. And because everything above the absolute zero emits in a temperature, you can see through the dust and you can really observe all these different temperatures and colors. Another use that we are now extremely familiar with is, for instance, an infrared thermometer, which we have now at home because of our pandemic situation. But essentially, infrared, it's a good way of measuring temperature, which is also why Webb has to be cold. Because if it's not cold, what the instruments will measure will be the heat and emission of the telescope itself. So you want to keep it cold, otherwise the signal from the astronomical sources could be drowned in the noise of the telescope. So we do have 4 science instruments in Webb, but today we're going to talk about MIRI, the mid-infrared instrument. And MIRI is, again, another example of a really good collaboration. It's a 50% European, 50% American instrument. This is a picture of MIRI, so you get a feeling for the size. The size of all of them is very similar for the instruments. So this is MIRI, and here to the right, you do have the primary mirror of the telescope, and on the back, this was actually the day where the instrument module, the ISIM with all the instruments, was sort of inserted in the back of the primary mirror. And MIRI is the one here, this one. So what can we do with MIRI? The coolest instrument, because it is colder. It is colder than the others. Actually, Webb, in general, like all the instruments except MIRI, are colder because it's a passive cooling. So They are cold because they are far away from the sun, around the L2 point orbit, and they are protected by the sun shields. The telescope is actually on this eternal shade. But MIRI, because it observes in the mid-infrared, the objective is to observe even colder and dustier objects, if you will. So the instrument needs to be at minus 450 Fahrenheit approximately, which is about 50 degrees colder than all the rest. And to do that, it has a separate independent cryocooler that sort of extends throughout the whole observatory. To give you an idea, our standard fridge operates at 40 Fahrenheit, so it's really, really a lot colder than that. MIRI will obtain images, spectra, and coronagraphy. So, imaging, you have an example here to the left, and actually this is the MIRI detector. This is a simulation, but this is how it actually looks like. So imaging, we have 9 different filters, so we will be able to take observations of astronomical objects in 9 different wavelengths, and with that we can do a lot of different color combinations and understand a lot of information. Here to the left you see these little boxes. These are our 4 coronagraphs. And so coronagraphy, as we saw before, is a technique where, as shown here in the middle, you can take a very bright object, say a bright star or a bright galactic nucleus, and put it behind one of these obscuration masks, either this little dot here or the crosses underneath. So when you do that, you actually block the central light. It's like simulating an eclipse. You block the sun, or you block the star, and then you can see what's around. And in this case, we have 3 little planets that are orbiting around this star. So it's a very powerful technique. And finally, we do have 2 different types of spectroscopy. And spectroscopy is essentially a very powerful technique that it's like the decomposition of light in different colors. It's essentially like creating a rainbow with your infrared light in this case. So you create the rainbow by dispersing the light with, for instance, a prism or some other dispersive element, and you have this light decompose in all these different components. And by doing that, you actually identify the fingerprints of the light. And by fingerprints, I mean different elements, different molecules, etc. With a spectroscopy, you understand the composition, the temperature, the density, and even the way the dust and the stars and the gas move in each of these objects. So it's a technique that allows us to really understand what's happening in the sky, literally. Going back to the instruments, I think it's a good to understand how the light goes in the telescope. So this is an animation of light coming into the primary mirror, reflecting, going into the secondary mirror, it's reflected again, and then goes into the ISIM, reflects again, and then goes into the ISIM module where the instruments are. Once the light gets in an instrument, it really has to travel with the instrument. So we're going to see now a simulation of some animation of a MIRI spectroscopy, and you will see how the light actually travels. Oh, I'm sorry, it's too noisy. It's just music, there is no audio about music. So you're going to see how a ray of light goes into the instrument, travels towards the region where we have the spectrographs, and then it starts to get decomposed in different colors and reflected and finally detected in our infrared detectors, mid-infrared detectors. So it comes here and it's actually deviated towards the spectroscope, the region where we have the spectrographs. And you're going to see a lot of different reflections. We have many mirrors and reflective surfaces. So here you start seeing the decomposition in different colors. And now each of these colors is going to be further decomposed. And we're going to create a good number of rainbows in this case. Here you see how it's really decomposing the light into many different colors. And finally, it gets into the detector. So these are the regions that break down the light in different components. Here are the dicrux, and grating wheels, and finally the detectors. So I wanted to show you a final animation where you're going to see the actual launch and the sequence we expect to have after launch. So Webb is now in the Ariane 5 rocket in the French Guiana, in the European spaceport. So this is liftoff and launch. And at this point, about 90% of the energy necessary to do this is coming from the boosters, the solid boosters. After about a minute after launch, Ariane breaks the sound barrier, then keeps on lifting, and approximately 2 minutes after launch, the boosters will separate and fall down in Earth because they are ready. They did their job, and the rocket can continue now with the main stage. This is about 3 minutes after the fairing opens and exposes the telescope. And approximately 9 minutes after launch, the main stage switches off and falls into Earth. And now soon you'll see how the second stage, the upper stage, will switch on and keep on adding additional energy that is necessary for the orbit injection. So after this, you're going to see how the telescope starts executing a slightly rotating movement, like a back and forth rotation. This is to maintain the thermal balance. You don't want the telescope, you don't want one side being exposed to the sun constantly. So you do this sort of rotating movement to keep all the thermal balance in check. This final separation happens about 27 minutes after launch. So it's relatively early, actually. And now, about minute 32, the solar panel deploys because we need to start getting some energy. And you will also see the telecommunications antenna being engaged. And by then, we also have the first mid-course correction executed. So you're going to see now a really accelerated sequence of the deployment. So these are the two pallets of the sun shield. They start getting, this happens about 3 days after, and the separation of the tower that you saw is about 4.5 days after launch. These are the two mid booms, and you see here how the tennis-sized court sun shield, it's really big, it starts getting tense and deployed. It has 5 layers. They slowly separate and get in position to start protecting the telescope from the radiation of the sun. Approximately 11 days after launch, the secondary gets in position, the secondary mirror. And finally, the 2 wings of the primary mirror, they get in place. So this is obviously very accelerated and quick animation. So this is a very, generally speaking, all these steps are really slow. They're executed very, very carefully. So things are, you make sure that one thing is finished before you engage and do the other thing. And I think this is my last slide. So launch no earlier than December 24th at 7:20 in the morning, Baltimore time. You can follow it on NASA TV. And after launch, we're going to have 29 days of traveling to the L2 orbit. On the way, there will be all this unfolding, switching on the systems and getting ready to prepare the instruments to do science. And 6 months after launch, we're going to be able to see the first images. That was my last slide. Thank you so much.
Thank you, Maka. That was a great summary of just what's going to happen next. And first of all, everybody, I want to just give a big shout to all 3 of our guests tonight for just telling us so much about how the telescope works, why telescopes are needed. Yeah, give them some love, give them some thumbs ups, because I didn't have to do anything tonight. No, I'm just kidding. No, seriously. So there were a number of comments and questions that came in. And I think, first of all, the most repeated question we've been hearing tonight is when will it launch? And of course, the answer is when it's ready. But right now, that seems to be no earlier than December the 24th. There's quite a bit. There's quite a bit more to quite a bit to go, but they've been able to resolve their latest issue with getting the ground support system to talk to the observatory, and they were going through a full up aliveness test, which I understand takes about 12 hours to complete. And then, if everything's good with that, then they're going to go ahead and encapsulate and put the fairing on. So it's getting real. It's getting very real.
It is.
So just a couple of quick questions that came in. Johnny Cheese was asking, what is the difference in Kelvin between the temperature of JWST instruments and the cosmic microwave background, the 2.73 Kelvin CMB?
So
yeah.
Miri is at 6.7 K.
6.7.
Slightly less than, yeah. And the mid-infrared instruments the near-infrared are about at 40 K.
Right, so it's not going to detect the cosmic microwave background. That's what Planck is for, yeah.
Exactly.
I think Planck was cooled to like less than a Kelvin or something like that, like a few millikelvin or something. Yeah, great. Let's see. Will it study the atmospheres of exoplanets? Keilan, I think you spoke to that earlier. Do you just want to quickly summarize that really quick?
Yes.
Thank you. That's our summary. Let's see. Can JWST take pictures like Hubble does?
Yes, but in different colors or different filters, if you will.
Right.
But yes, it will take. There are 3 instruments, MIRI, NIRCam, and NIRIS, that have imaging capabilities.
Excellent. So there will be images. They'll be color coded to let us basically see in the infrared.
Exactly.
But there are going to be some really spectacular images, as I understand that. And to make those images, you need mirrors. And CO185 asked if those mirrors are all adjustable. I see now why vibrations were a big deal. Yeah, vibrations are a big deal. So how do we adjust those mirrors? Can they be? What if we have another Hubble problem when it was launched with when it was grounded the wrong prescription? What do we do then?
May I?
Yeah, please, Mako, go ahead.
So with Webb, we have the primary mirror, and it has 18 segments, as we saw in Parviz's presentation. So each of these segments has actuators in the back, and the actuators allow to do very fine, precise movement, so you get the perfect shape of the mirror. If you compare this with Hubble, well, Hubble was a monolithic mirror, and it was not as thoroughly tested. So with Webb, we have already done ground testing that demonstrated that we can actually put the mirrors in the, if you want, perfect location to have a really good image. So at launch, at the very beginning, we have 18 segments, and when we point to a star in the sky, we're going to get 18 different points. And then there will start a really long process of iteration, observing, moving the little mirrors. So those 18 points converge in a perfect, very sharp star. And then we can keep on correcting as necessary.
Okay, so the mirrors are adjustable, which,
unlike
Hubble, which was a single monolithic mirror, it was grounded the wrong shape, and we had to put in corrective optics. So, great. And also, just want to say a big thanks to, let's see if I could just find it here. We just got a very generous super chat from Nipul. If I could just find it here. Okay. So, how long till we start seeing data and pictures? So, Maka, you mentioned that it looks like it's going to take about 6 months just to get everything deployed, unfolded, and cooled down to the operating temperatures, right?
And no, all that takes a bit less than that, but then there are weeks dedicated to. We have, for each instrument, we have observing programs that are dedicated to demonstrate that the instruments are ready to do science, are ready to be calibrated. To just, if you want, it's like putting put them in a optimal configuration after launch to do science. So beautiful images and beautiful data of astronomical objects, it will be 6 months after launch. I think probably before that, the public will get to see, I don't know, maybe when the mirrors are in the perfect configuration, some nice image, but the nice images will come really 6 months after launch.
Great. And Joe Fink, thank you. Joe Flink, thank you so much. This turned out to be the in-depth JWST primer I didn't know I needed. Thank you all very much. Thank you very much, Joe. I appreciate it. And by the way, we are trying to prioritize Super Chats. We're trying to get to as many questions as possible. Please note that if you are a student of mine, you may not Super Chat me because you are broke. But thank you very much for helping to keep the lights on. Yeah, you know what? Google's right about that. You know, it's fun to be cynical about JWST's launch date, but you have to respect the gigantic risk they're taking by placing such a project at a large Lagrange orbit. Yeah, I would say that would be exactly it. Yeah, and there was a follow-up here, which I thought was great. Gigantic risk is an understatement. Well said. Well said. I know there was like a bunch of other questions here, and I don't want to take up too much of our guests' time tonight. One thing that Red was asking is the usage of JWST planned out for years already? How is that time decided and prioritized? That's an interesting question. Keilan, since you've had to run through the gauntlet of getting time on Webb, how does that work?
You have to apply, so you have to propose a project. And so usually there's cycles that you can propose them for. I'm not sure if it will be every year or what they're thinking of doing for JWST, but at least this past year for cycle 1, there was a call for proposals. So you kind of put together a team of scientists, put together an idea, write a really strong proposal on what instruments you want to use and why. And the people who are reading your proposals are actually doing it double blind. And so I thought that was pretty cool this year because 8% of the people who received time on JWST for cycle 1 were actually grad students. And normally that percentage is much, much lower if it weren't double blind.
Oh, that's cool. So we're getting a pretty broad cut of the, actual astronomical population out there. So that's fantastic. There was another one. Oh, okay. Well, this is a question I've seen come up quite a bit. How much is launch insurance? It turns out Geico does not insure launches because they don't know, they don't want to cover 10 bill. But actually, I can speak to that because I happened to was watching some conversations of the NASA administrator talking about this, and basically NASA does not insure. I mean, they don't take out insurance policies. They self-insure. They're backed by the federal government, so that's sort of the idea. But no, there's really no way to underwrite a launch like this. And what risk do you expect and why? A lot. There's what? How many deployments are there? Is it 344 deployments? I think is what it is, individuals. Anybody know? It's a lot.
It's a few hundred, what they call single points of failure.
Yeah. So if any one of them doesn't work, well, it doesn't necessarily mean it's a complete failure. Not necessarily.
No. Like for instance, the primary mirror, like the two wings, if one of those wings doesn't deploy, it has an impact in the resolution, like the detail the telescope will be able to see, but it's not a catastrophic event. And part of the reason why there were delays and all that is because the whole telescope has been really thoroughly tested, and there are a lot of procedures and backup plans in case something goes, gets complicated, essentially.
Of course, right. So there's some risks that can be tolerated. I think probably the biggest risk that we really do have with the Webb, I mean, even with the sun shield, like even if the sun shield doesn't perfectly deploy, there are some workarounds or mitigations to that, or that maybe limits some of the science you can do, but doesn't completely stop the show. But if that secondary mirror does not deploy, that, the mirror out in front. If that does not
Yeah.
deploy, there's no telescope, right? I mean, that would be bad.
Yeah, but that's quote unquote just an arm that has to deploy, quote unquote, right? So I think, yeah,
Okay, good.
we'll find out very soon. But I think everybody's confident that things will work well.
Well, they've tested it within an inch of its life, and I think that they're not going to launch it unless they know it's ready. And clearly, if it's sitting on top of the
Absolutely.
rocket, waiting to be sealed up in its fairing, it's ready. It is ready. It's just there was some hiccups getting some tests run just to make sure everything was good to go. But it does look like, and yeah, Johnny, yeah, there is some redundancy on board. Engineers are very conservative. They're going to put in a lot of what's called margin, a lot of ways for it to work. And this is the other big common question. Will there be a NASA mission to fix it, as there was with Hubble at least once? And the short answer appears to be no.
No, because not only is a million miles away, which is a challenge in itself, but it was never designed with that idea in mind. Hubble was designed with the idea of sending astronauts and having the ability of changing one instrument for another, etc. But Webb is not designed with that sort of servicing spirit in mind. So I think future missions probably will, but for Webb, I wouldn't expect that.
Yeah, it makes sense. Just to maybe show you just a little bit of just where you're at, just to kind of show you how this stacking went. If you don't mind my sharing you guys just some very brief slides really quick, but here's a sequence of images that ESA released. This is Webb sitting there in the final assembly building, and it was trucked in after being fueled up, and it's sitting there in between some portable HEPA filter walls. Then it got hoisted up in this beautiful anxiety-ridden photo. I just love this image of it just dangling above the floor. Then you see here in this image, it was actually brought up through that great big hole in the ceiling above. Now it's on the floor below. Then it was swung over. Now that if you look there, you're going to see there's a hole it's going right through, and that hole is the hole that leads right down to the second stage, the top of the second stage of the Ariane 5. You can just see, I love this image because it just shows you just how big this telescope is. It's everyone's going about like, why wouldn't SpaceX launch this? This is why. Or this is one of the reasons. Well, actually, SpaceX wasn't even a thing when this was designed, but SpaceX's launch fairing isn't large enough to accommodate Webb. It's a 5-meter fairing. This is a 5.4-meter fairing, and it just fits. It just fits inside of that fairing as it's being lowered, and this is where it is right now, sitting on top of the second stage. And this is on a platform that's right there at the very top. So, you know what? I mean, this is how it's done. The good news is that things have now gotten sorted out with the integration and aliveness testing. I saw it tonight on Twitter, and I know if it's on Twitter, it means nothing, but this tweet came from none other than the CEO of Arianespace himself, and he said that encapsulation is underway, that they are sealing Webb up in its fairing. So this is we're on to something. We're on to something pretty big here, folks. And what is everyone most excited about, really quick, as we kind of go around the room? Parviz, what are you looking forward to learning about with Webb?
Well, I want to learn how frequently we find planets that are like Earth out there.
Earth-like planets, yeah, definitely.
We have another place to move to once we're done bollocksing up this planet.
Keilan,
you want to make a what's it called, a generation ship, like the Nauvoo?
Let's see. And a super chat from Yvonne Berger, am I the only one feeling a bit anxious about this project? The fact that it can't be repaired is a leap in human confidence. Well, it's is it a
It's
leap?
just you.
It's yeah. No one else is worried.
No one else is worried. What, me worried?
Oh my goodness! Thank you very much for that super chat, and thank you, Legato. And yeah, I think we're trying to address your question right there. What are some of the things we're looking to get to first? I know that first are going to be those early release observations, something for the public to see, and apparently NASA is or not even NASA, the people at the very, very top of the Webb program are keeping their mouths shut. They're going to release some images all at once, and it's going to be a great big surprise, but they're going to be very, very, very pretty. Which is nice.
Exciting.
Which is nice, yeah. Let's see. And so, Keilan, how about yourself? What are you looking forward to seeing with Webb, apart from your science? Okay, your science is definitely worth it, yeah.
I'm actually curious what they find with some of the high redshift galaxies, because the farther you're able to see, the further back in time we go, and I'm actually kind of like interested to see what comes from that.
Great. And Maka, how about yourself? What are you looking forward to with Webb?
I'm looking forward to the surprises. Because with this, honestly, with this telescope and it's like when Hubble was launched, like there were many things that were surprising. I'm looking forward to something that is like, whoa, we didn't expect this, and now we have to figure it out. And the high redshift galaxies.
Oh, and the high redshift galaxies. Being able to see the first galaxies and the first stars forming in the universe would be kind of nice. That is actually why it was built in the first place, so that's fantastic. Well, we are coming up right now. We're looking at a Christmas Eve launch potentially. If they cannot launch on Christmas Eve, ESA has said they will attempt a launch on Christmas Day if necessary. After that, they'll have to wait at least one day because they have to recycle the liquid oxygen propellants, and then they can go again on the 27th, 28th, recycle. They could do this all the way out to January 6th, at which point they got to wait because then the moon starts to get into the way and they will have a deflection due to gravity. So that could be a problem. Do we know if there's any official time slot for an ultra deep field image like JWST? Thank you, Patrick, for the super chat. Really appreciate that. Yes, there will be a James Webb ultra deep field, or rather it's going to look into the deep field. Do you happen to know when that's going to be? That's going to be cycle 1, or is that
cycle 1? There are a few programs that will take deep images of some of these Hubble deep field regions, because you want to go to the same place just to build up on the data there. But I think as deep as the ultra deep field, that will have to wait for another cycle. Cycle 1 is more for, learning about the instruments and getting like a first feeling for that.
I see. So basically, yeah. So there'll be a lot of calibration work, just getting everything running and just really knowing what these things can do.
Right. Yeah. And we'll get deep fields, but maybe not as deep as the ultra deep field.
Right. Well, John Curtis, thank you so much for that $10 super chat, man. Really do appreciate it. He's looking for a planet that's completely covered by water. That's all he wants for Christmas. Let's see if James Webb can get that to you. I hope so. That'd be cool. Can there be a planet purely ocean? Any reason why there couldn't be?
We have one in our solar system. Not a planet, but a moon. So.
Okay, but that's frozen on top.
Could be
right?
possible.
Exactly.
Water, though.
Yeah, that's true. A lot of water. Yeah, cool. Well, now I also understand there's one more thing that I should kind of wrap this up with, and that is, obviously, yeah, we've got some things to do with Webb. I just want to talk briefly again about the launch. We hear a lot of complaints and frustration about delays and so forth. The fact of the matter is that this is James Webb. This is not every mission has a certain amount of risk that managers are prepared to tolerate. Not James Webb. There is no risk that the management will tolerate. So they will go through every single check. They'll do whatever needs to be done. And if it means launching on Christmas Eve, then they're going to launch on Christmas Eve. But here's the good news. And this is what I think has been suggested on Twitter. And I got to give a huge shout out to Science Socks on Twitter for coming up with what I think is a brilliant idea, and that is to see if the big guy himself can haul it on up there for us, right? You know, just open up everything. In fact, we could even just pre-deploy. I love this idea. We could pre-deploy it on the ground and avoid all those points of failure and say, hey Santa, we've all been really good this year for these last 30 years. What do you say if you just sprinkle some magic dust on there, don't get anything in the optics, and then take it on up to L2 for us? What do you guys think? Would that work?
Yeah.
It works for me.
It looked like it was being deflected by the moon there in that picture, though. So Santa has to keep pushing his sleigh to...
Right, exactly. So we got one more super chat here, and then we're going to have to call it a night, folks. But Ken, how are particle physicists going to benefit from James Webb? I wish we had a particle physicist here to answer that question. Anybody know? No.
maybe an indirect thing, like maybe if James Webb makes some discovery that it implicates a certain kind of dark matter, then that so maybe indirect.
I think so too. Yeah. So hopefully we will see Rudolph's nose from L2, and I agree with you, Rad. No coal in that telescope. Hey, everybody, thank you so much. We've gone, this is actually the longest live stream I've done in a very, very long time. It has been a joy to talk with you all and just to wish everybody a very safe and happy holidays to everybody. May you all have a very safe and healthy Christmas and New Year's and a Festivus for the rest of us, but most of all, a happy and healthy launch to JWST. I want to thank again my guests tonight, Keilan Koch, Parviz Ghavamian, and Macarena Garcia Marin, for joining us tonight. And if you would like to join me on this journey to this incredible universe of ours, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, my friends, stay healthy and have a wonderful holiday season. And above all else, stay curious, my friend. Good night. Once I figure out how to get this thing to shut off, we'll say good night. Oh, goodness. You know, this is just, it's like the long goodbye. You know, I've lost my cursor. I can't see where my cursor is anymore. Okay. And now I think I'm going to go ahead and finally call this thing good night and stay curious.